Welcome to the third installment of the APU series. In the previous two parts, we started the APU engine, connected the APU's electrical and pneumatic power to the aircraft systems, and used the pneumatic power to start the main engines. Then we selected the main engine power for the aircraft systems and disconnected the APU power. While the APU's electrical power is easy to disconnect with the help of breakers inside the power panel, the pneumatic power disconnection is a complex procedure that starts with closing the APU shutoff valve. When the shutoff valve is closed, the APU controller will close the inlet guide vanes and reduce the bleed output of the load compressor. But airflow has to be maintained through the load compressor to prevent a compressor surge. Since the APU bleed air is not being used, the output flow from the load compressor drops and pressure increases. An increase in discharge pressure can reverse the flow and damage the load compressor. To counter this, the APU is equipped with a surge control system. The pressure sensors send the load compressor output pressure data to the APU controller. When the discharge pressure reaches the calculated threshold, the controller sends a signal to the fuel pump to operate the surge control valve. The pressurized fuel opens the surge control valve, and the air from the load compressor is passed through a duct connected to the engine exhaust. This keeps air moving through the load compressor and prevents compressor surge. Before moving on to the in-flight performance, let's complete the ground procedure by shutting down the APU. When the APU start switch is turned off, the APU controller initiates the shutdown sequence. The shutdown is not immediate. The APU goes through a 105-second cooldown period before shutting down. In the initial 15 seconds, the APU controller keeps the engine running at 100% RPM. During this time, it ensures the APU bleed is unloaded, the inlet guide vanes are closed, the surge control valve is open, and the generator supply is disconnected from the aircraft systems. After 15 seconds, the APU enters the second phase of the cooldown period. The controller reduces the fuel flow into the combustion chamber and drops the engine speed to 70% RPM. Once the cooldown period is over, the controller cuts the fuel supply and stops the combustion. The engine experiences rapid deceleration. The fuel supply from the fuel tank to the APU is stopped when the engine reaches 15% RPM, and simultaneously, the APU inlet door is commanded to close. The right engine failure results in a loss of power in the right electrical panel. With only one generator available, the electrical load management system will deactivate the non-essential loads and use the left engine generator power to activate the right essential buses. As the right engine bleed is unavailable, the air supply computer will use the left engine bleed to power the right air conditioning packs and other user systems on the right side. With a single engine failure, the APU is only required for its electrical power source. Let's turn on the APU. Selecting the switch to the on position opens the APU fuel feed valve, activates the APU controller, and opens the inlet door. The start position of the switch will crank the engine. The aircraft's pneumatic power is available. The APU controller will use the left engine bleed air to start the APU. The controller commands the air supply computer to open the shutoff valve. The bleed air from the left engine travels to the APU. The check valve prevents the engine bleed from entering the load compressor section. The APU controller opens the air starter control valve, and the bleed air operates the air turbine starter. The air turbine torque is transferred to the ratchet wheel, from the wheel to the pawl clutch mechanism, and from the clutch to the drive gear connected to the engine gearbox. At 7% RPM, the controller activates the fuel flow and ignition system. The air starter control valve is closed at 55% engine RPM, and the air turbine starter disengages from the gearbox rotation. After a successful engine start, the air supply computer closes the APU shutoff valve. Once the APU's electrical power is available, the generator starts supplying power to the load management system, and the aircraft's full electrical power is restored. The APU bleed is unavailable above 22,000 feet. As altitude increases, the air density decreases. The bleed air output of the load compressor is insufficient to meet the pneumatic demands of the aircraft. Therefore, above 22,000 feet, the APU shutoff valve remains closed, the surge control valve is open, and the inlet guide vanes stay in the closed position. As the aircraft descends to 22,000 feet, the APU bleed is available, but the air supply computer will continue to use the left engine bleed. If we disconnect the engine bleed, the air supply computer will open the shutoff valve to use the APU bleed. To meet the aircraft's pneumatic demand, the APU controller will close the surge control valve and open the inlet guide vanes. The APU controller measures the engine RPM from the data provided by the speed sensors. The speed data is critical for starting and controlling the engine. When the APU supplies electrical and pneumatic power to the aircraft systems, the workload on the engine increases, and as a result, the engine RPM reduces. To compensate for the drop in speed, the APU controller will use the fuel metering valve and increase the fuel flow into the combustion chamber. By controlling the fuel flow rate with precision, the controller maintains the engine speed at 100% RPM. The design of the APU to run at 100% RPM has both electrical and pneumatic advantages. The engine speed determines the APU generator output frequency. Governing the engine RPM at 100% ensures the APU generator output frequency remains constant. This allows for a simple generator system with a significant weight reduction when compared to the main engine generator. The output frequency of the left engine generator will change as the thrust of the engine changes. Therefore, the main engine requires an integrated drive generator system. The IDG is a combination of a constant speed drive and a generator. The CSD ensures the generator is always driven at a constant speed as the engine's RPM continues to vary. This increases the weight and complexity of the generator system. The APU bleed usage is relatively easier for pneumatic operations, such as starting the main engines. Since the load compressor at 100% RPM provides the necessary duct pressure to start the main engine, the air supply computer uses the APU bleed even if the opposite engine bleed is available and selected. To perform a cross-bleed start, the APU bleed has to be deactivated. When the main engine is at idle speed, the duct pressure is insufficient to meet the heavy pneumatic demand of the opposite engine starter. In a cross-bleed start, the thrust of the running engine has to be increased. This makes the procedure complex and increases the workload. Join us in the next part of the series as we explore the APU's critical function when the Boeing 777 suffers a dual-engine failure. Thanks for watching.